it seems pertinent at this point to kind of talk about why one would even make a fuss about, exactly how this happens. Why do we care about the nitty-gritty details? It's very important a lot of times to be able to know the mechanism of how things work. One, in order to actually even predict the final products, like we saw in the carbocation mechanism. If you didn't know the carbocation mechanism, you would never know that there was the possibility for some kind of a rearrangement. And so just like with the carbocation mechanism giving insight into the structure of the final product, being able to know that the bromonium ion is the mechanism for Br2 addition gives a lot of good insight into why we get certain products and why we don't get others. So just for a second, let's kind of go down a hypothetical path in this weirdo universe where Br2 didn't actually add via the bromonium ion mechanism. And I'm going to give you a new molecule and just kind of have you react it with Br2. So just like before, we have Br2 reacting with our alkene. It's a slightly more complicated alkene, but let's just say for a second that you actually didn't believe me. You thought that this whole bromonium ion was kind of baloney, or you didn't think that it would ever happen this way. So how would you prove me wrong? Well, then you would propose some other kind of mechanism, like maybe this reacts the same way as HBr. And if it reacted the same way as HBr, then the first two arrows would look a little bit more akin to something like this, where we're making a bond and we're breaking a bond. Just those two arrows, very similar to whenever we had HBr. We had HBr looking kind of like this, and this is exactly the way the HBr reacted with the alkene. But instead, now if we just remove the hydrogen and replace it with the bromine, what would happen? So go ahead and pause the video and try to predict the structure of the intermediate that we would form in this case. So pause the video and then unpause and see if you get the right structure. Okay, so if you had gone through this mechanism at the very beginning as if it was HBr, that would mean that this molecule would go through some kind of carbocation mechanism. And then if that's the case, you have to kind of choose in a very Markov-Nikov way, do you want to put the bromine on carbon 1 or carbon 2? And that choice is very, simplistic at this point in our OChem lives, because we know that we always want to strive towards that more stable carbocation. And so here, you could have put bromine on 1 or 2. If you put it on 1, you get a secondary carbocation. And if you put it on 2, you would get a primary carbocation. So the choice is very obvious that this is what you would want. You would want to put that bromine on carbon 1. So if this was the case, red light should probably be going off in your brain right now that, oh, wow, we have actually the possibility of 1,2 hydride shifts. So we always have to be on the lookout for that. So we have a hydrogen that's, vicinal. We can use that new term now. It's vicinal to carbon 2. And so because of that, we could do this 1,2 hydride shift type of secondary mechanism. So we could move this hydrogen over by 1. And so this would be the 1th position, and this would be the 2nd position. So then we could redraw this mechanism and have this guy come over here, and bromine should still be here, and then we would get a positive charge on here. And so now, after we redo this mechanism and we've done our hydride shift, we get another carbocation that's more stable. So this is a very good reason for this molecule to try to do this hydride shift, because it's adding, stability to the intermediate. So now that we've added pretty much as much stability as we can get, tertiary carbocations are about as good as you can get from what we know so far. You can move on to having this last attack step. So we have a bromine minus still in solution, and it could attack that positive charge, and specifically that carbon right there. If this molecule reacted with Br2 via a carbocation type mechanism, what we would find is that these two bromines are no longer vicinal to each other. You actually have 1, 2, 3 carbons that span the gap between the two bromines instead of just 2. And this is definitely a different molecule than the molecule we drew up above. And so if you were to say, well, I don't believe you that this molecule, I don't think it goes through the bromonium, I think it actually does this little addition thing. And this is actually really good. You should definitely question what you're told always. And so if you questioned it, which would be a fantastic thing, and if you thought it would go through this, then by this mechanism's logic, we should at least get a little bit of this product, where we have 3 carbons spanning the gap instead of just 2. And what we would find is, if you did this reaction in the lab, you would find that this molecule would be present in 0% of your solution. So it's, a very strong piece of counter evidence that, it doesn't really support this mechanism. And, the fact that you get 100% of this type of vicinal molecule is very good evidence to support the hypothesis that, you get this bromonium ion mechanism.